Okay, recording is in progress. Okay, so thanks for coming to the second meeting. And today I will be directly talking about integrals, Grassmann integrals. Just to remind, previously we were talking about the notation introducing anti-commuting variables in this notation with a big 0 here. So, and then this usually will be going JK from 1 until L. So we have L such anti-commuting symbols. And today I wanted to say a couple of thoughts about, I wanted to say a couple of thoughts about introducing Grassmann integrals. So in short, the definition, I think Berezin was the first one to introduce it. And we will be using this notation here. And those not 0, sorry, delta JK. So this notation is suggesting that we are doing integration, but as everybody knows, this looks a little bit more like a derivative, because if I integrate dx x squared, then I should get x squared over half plus c. But for Grassmann numbers, because of anti-commutation, gk squared is 0. So what do you do for an integral? And instead, this looks a little bit more like a derivative of the x function, and then you get 1. So that's something that I would like to discuss after we finish the recording. Basically, yeah, we can brainstorm a little bit why this is integration and derivations algebraically and so on. But today I wanted to focus a little bit more on saying how this definition is already enough to get a lot of properties that people just write down for Grassmann integrals. And I wanted to show a couple of thoughts about how this stuff comes about. So I will be denoting a Grassmann algebra on L symbols. We can just write it down like this. So it's generated by L symbols, and then we can say that this has some Grassmann equivalence relation, which I don't know how I should denote it, maybe with a bar. And this anti-commutation relation here is G bar. So basically all monomials that can be connected through anti-commutations, we are setting to be equal. And I'm telling you that because this is the full algebra, so it's like a span of all monomials. But I can also look at the linear vector spaces of the generator. So the linear vector space of generators, I would just say that this is the complex span of vectors that I say are G1 until GL. So in the algebra here, we have multiplication and addition. And here I only have addition. And if I will start multiplying them, I will go higher order. But now I would like to focus on this GL1 to show that already this definition is creating an interesting definition for us for the integrals. So the first thing I wanted to say is that once we have this definition, we could say that basically GK is a linear map. Okay, so it's a linear map that we can say that is, for now it will have a restricted definition, and then we can extend it, but we can go from the space, linear vector space of the span of generators to complex numbers. Yeah, why this is clear is because we will say that this is also a linear map. Linear map, okay? So for example, I can say that GK applied to alpha j gj, summation over j from 1 until L, that this is, so now I'm just using C linearity. So here I'm trying to say, okay, let's build a definition of this Grassmann integral from as few axioms as possible. But first of all, it will be a map. And for now, I'm starting from this linear vector space of generators. And now I have here gk, and what I'm integrating is gj. And then I need to sum it over from j equals 1 until L. And this is, as I was saying before, this is defined to be the Kronecker delta. So what it gives me is alpha j. No, not alpha j. The dummy index goes away. Okay. Alpha k, and that's it. Yeah, because we have this kind of derivation removal here. Okay, so this is to say why it's interesting to define, first of all, the Grassmann integral as being a mapping from the linear vector space spanned by the generators and going into complex numbers, because anytime I encounter some Grassmann number, I will either drop it to 0 or I will yield here some complex number. So it's always, so the image of this integral, so to speak, will be complex. And the next problem that I want to show is what happens when I define mg. And mg is defined in the sense that mg and the kth element of the vector is a summation over j from 1 until L. And then how to order the indices, maybe I will order them like this, and gk. First thing I would like to show is that basically gk prime defined in this way is again a set of generators of a Grassmann algebra, which we can check explicitly. Basically, anti-commutation is C-linear, M is some complex L by L matrix. Actually, we should say that here it's not just a complex matrix, but it's an invertible matrix on L, on dimension L. And then we get K prime prime, a simple computation, whoops. A simple computation, J prime, MJ, MJ, yeah, that's the dummy index here for the summation JK. And the second one with the J primes, K prime. And because of the linearity of the anti-commutator, we have the anti-commutation here. And they are all anti-commuting, so we get a 0. And I need the invertibility so that I don't drop the dimension. Because if I would have a lower rank matrix, it would mean that some of those new J prime symbols are linearly dependent, and that would be a problem. Okay, so now I'm setting up something where actually what seems to be interesting is to consider what happens if I integrate into such a Grassmann expression. Yeah.
Marek, I think there's something wrong with the indices, no? Like you sum over J, but then the J only appears in the matrix, not in the G. Is that correct?
Yeah.
I feel like G and K should be flipped, no?
Here should be JJ prime because that's the newly introduced indices, and here I should have J.
Yeah, no, it makes sense.
And now the order is kind of funny. No, the order is correct. So yeah, thanks. Yeah. And this is different. Yeah. So this is a bit different from other algebras, but it's very similar to stuff that we will encounter for fermions through Bogoliubov transformations. Yeah. So now I'm running through it quite quickly, but the point is to say that that this operation here that I'm defining for a different Grassmann number and the Grassmann generators, it has to be somehow related to the regular integral that I defined, okay? And the way to think about this is that I have a linear map that I denote by this integration into JK symbol. And now I define it, so to speak, on a basis. And then I can rotate the generators by a GL matrix. So I make a basis transformation of this here, the one space of those Grassmann numbers. And now I have an integration into a different Grassmann number. And then how are they related? Yeah. And there are different ways to prove it. And one way to prove it is to directly have the right ansatz, or so basically let me write this down. This will be our result. I can show you how to get this. And my point here will be that making those simple, if we make those simple definitions, you can get a lot of structure of why those integrals have to be like this and not something else. And here the integral, okay? So basically the integration into this transformed set of generators is a linear combination of integrations into here GJ. Thanks, Alex, for the indices. Yeah. And now first of all, how to think about it? Well, basically, we want those consistency relation. So it's actually consistency relations. It's a system of consistency relations because we have to have some consistency relation for all k from 1 until L. Okay, and the second thing is why we want them is because the span of G1 until GL is the same vector space as the span of those transformed generators. Yeah. So it's the same vector space. So the integrals should somehow be related to each other. And again, the definition of those transformed Grassmann variables here is just a linear combination of the previous ones. It's an invertible matrix. So those linear spaces that are spanned are consistent with each other. And this is what I call this G1 space. For fermions, this is the equivalent of the single particle space. Okay. And so if this is the same space, so I was defining the integral to be a mapping from this G1 space into C numbers, and this one also, and it's a linear map. So this is exactly what is this basis transformation here. Okay, so how can we show this? And the ansatz to show it is to consider, and I will be considering K and J, Kj from 1 until L. So I consider like L squared many relations like this. And for all those parameters, I want to ask what's the integration into this transformed Grassmann number of the previous Grassmann number. So I define the integral in the basis. In this basis, we have the definition Gj Gk is delta Jk. Here the order of indices doesn't matter. And we want to ask what is this thing. And what we can say is that mgk, so basically we can invert the relations that I was writing on the previous page, and we can write let me undo this. The inversion of the previous transformation, then I will take Jk and Gk prime, where Gk prime on the G was the summation from Mjk and Gj. Here I might be messing up the orders of indices, but that's roughly this. So now I can basically write here that Gj is m to minus 1 gk. And then here I will not write gk prime. I will directly write m on g. And here I will need k prime from 1 until L. And here I have k prime as well. Yeah. So because of linearity, I can take it out. Summation over k prime, mjk prime with a minus 1 here. So I'm taking the matrix element of this one. And here I have an integration that we will postulate that holds in every basis. So we get some basis independence of the definitions, and that's our consistency relations. So we would like to postulate that so the story was I defined this in a basis. I defined it in the initial set of generators. Then I said that because we are using invertible matrices, then this G1 space is the same. So we need some consistency relations, and we want to define this integral in any basis. So the natural definition is to say that this is again a Kronecker delta. So we want to define this to be the Kronecker delta of kk prime, yeah? And if I do this, then what I get for this integral is that this is a summation. It's not a summation anymore. I get directly m minus 1, and the summation over k prime becomes k. So I get j k, yeah? And the only thing that is missing from the transformation that I was writing is that we have those integrals. But this is like equality of a map. So this is equality of linear maps, yeah? And this is checking the equality, checking equality on a basis. Yeah. So then by linearity, we see that those maps have to be equal. So that would be our conclusion here. Yeah. So that's maybe a fast way, but that's something to think about. That once I define the map to be linear on generators, then this linearity tells me quite a lot. And then I realize I can make those GL transformations and transform the generators into each other, but they will span the same space. So then I need to have a natural way to define this. And this is then in some way a basis independent way, because any basis can be related by this GL matrix. That's sort of the invariant transformations of the Grassmann algebra here. Okay, so it's not really a proof. You would still need to say, I define this linear map to be behaving like this, but in some way it's a natural definition, yeah? So yeah, and that way they are all consistent. So we can discuss what follows from which definition. So I will review this in a second. But okay, now we understood the transformations. That's the important equation. And I want to finish by saying one more thing, which will maybe take more time, so we might need to take a break. But now this G1 space is a subset of the entire algebra, because it's just a summation without multiplications. And now I need to start defining the full algebra. So I want to set up some notation. So I will take a cube on L01 symbols, and I will take from that a binary string of zeros and ones. And from that, I will define a Grassmann word, which is an ordered product, where I either take a Grassmann variable or I don't take it, depending on whether I have 0 or 1. So g to power 1 is g and g to power 0 is 1. Okay, so that's a Grassmann word. And now the question will be how to start define. Okay, so once I have this, then I can define this to be the complex span of those g mu's. And mu in the Boolean cube. Okay. So now the question is how to extend this integral gk from the domain g1 to gl. And again, we will need to get some more consistency relations, and what we will arrive at is those anti-commutation relations for Grassmann integrals. And what we should view it again is that okay, so we want to have in general an integral over g mu, or wait, how? So now we will have a lot of maps. Those maps will be indexed by the word that we are using. And we should define what it means to be integrating here some other word here. Yeah. And so we will have to define all of those basically to be a lot of maps. But the way we should be defining this is that G mu we should define as a composition of G L, the last one, mu L. So I will either apply this map or not, depending on the 0 and 1 content of mu L. Then I have GL minus 1 to mu L minus 1. And then I compose all of them. So this composition you don't see written down anywhere because people don't focus on this being a linear map. But basically we should say, okay, the integral which involves more Grassmann numbers is just an ordered compositions of applying those linear maps that we were defining. And now the question is how this map is acting. So I have GK, and how this map is acting on G mu. We just need to consistently define it. And the way to define it is the best way is to do some sort of sorting. So for example, if we anticipate this composition, GJ, and then I would be in, so I compose this map. This is a new map, just a composition of two of them, GJ, GK. I would like this to be 1, right? And also once I define this to be 1, the inverted ordering of those Grassmann integrals here should be GK, should be the same as on the input GJ GK. They should stay linear. So if I write here minus GK GJ, then I should get minus 1 here because I just put out the minus sign. So this is how we define this linearity, and that's why I was insisting on ordering this stuff. Because once I order it, I can define the action on monomials. So that's the first thing we would be defining. And in some way, this is implying that symbolically we can write GK, GJ, that basically those maps anti-commute with each other. Okay.